Right, so looking at our do now, we're asked to find which expressions are equivalent to 3h plus 9. So we're looking at also needing to use h is equal to 2 in order to prove this. So when you look at this, we have a couple different ways we could write this 3h plus 9. When we think about 3h plus 9, one thing we definitely know that we can do is to distribute, and that's going to give me 3h plus 27, so we can hypothesize here that B is correct. One thing that we can do is we're supposed to use h equals 2 to prove this, so 3 times 2 plus 9, parentheses first, 3 times 11 would give me 33. Coming over here, if we plug in 2 here, 3 times 2 plus 27 is supposed to be 6 plus 27, which would be 33. So that indeed does check and prove that that is correct. We also know that this could be 3 groups of h plus 9, which could be h plus 9 plus h plus 9 plus h plus 9. So again, plugging in 2, this is 2 plus 9 plus 2 plus 9 plus 2 plus 9. And this is 11, 11, and 11. And we can see that relationship between the 3 times 11 upstairs and the problem above. So this is 33, and that's this answer down here. And let's go ahead and disprove these other two, kind of off to the side over here. 3 times 2, this is 3h plus 9. 3 times 2 plus 9 would be 6 plus 9, which is only 15. Disproves that answer. Then h plus 9 times 3 would be 2 plus 27, which is only 29. Alright, let's look on over and look at our aim for today. Alright, today's aim, Kipsters will be able to use inverse and identity, and any order, any grouping, to simplify expressions. Alright, so as we look over here, it says we're going to be exploring some things here and there, so we're going to pretty much go throughout this entire lesson. You're going to get some ideas, get some chances to practice, work with your partners, then move on. Alright, so looking at this, we want to fill in the center column of the table where the opposite is given. So again, we know when we're talking about opposites, we're talking about sign differences, and then we're going to be writing over here the proof of the opposites over here in the right hand column. So this should be something that's quick and easy. We have one example. The opposite of 1 is -1, and our proof here is 1 plus -1 is equal to 0. Try and go through this entire table right here and determine what your opposite is and your proof of the opposites. So as we jump through these first 5, these are all pretty self-explanatory. The one thing that we do notice here is that we know that when we have inverse operations or we have inverses, opposites of each other added to each other, that they lead us to the identity, the additive identity. Sometimes we'll call this the additive identity property of 0. And we know that that's just that we're talking about that opposites added together lead us to that value, that one and only single value that we could add over and over again. We're going to explore that again here in a second. Now this next one is the one, these next couple are the ones that I really want to talk about in order to think about what value we're really getting from filling out this chart. Now these two, when we look at them, the opposite of this would be this. We can think about the opposite of this also being distributed in as a -1. And that's really thinking about this being a -x plus a -3. And the reason we know that would be opposite is because we want it to equal 0 here. And so our proof here is that we would have x plus 3 plus this -x plus -3. And as we come through here, we rearrange this x plus -x. That's going to be 0 plus 3 plus -3. That's going to be 0. So that's the one that I really want us to think about here, is we can start seeing this relationship that we want the opposite of x plus 3, so we can write that in parentheses as the opposite of this group, x plus 3. And we see that in order to make this actually be the opposite and add up to 0, that must mean that it's equal to -x plus -3. So coming over here and looking at this one, this is like a 3x plus a -7. So in order to have the opposite here, we need the opposite of the positive 3x, which would be a -3x, and the opposite of a -7, which would be a positive 7. So again, we would see that that distributes in, changes the sign, just like as if it were be multiplication by -1. So when we come over here and write our proof, we start with 3x plus -7, and our opposite would be -3x plus positive 7. And rearranging that, that just shows us more clearly -3x plus -3x, that's 0, plus -7 plus positive 7. That's going to be equal to 0. So again, when we see this, we can rewrite the opposite of a group as negative opposite of the group, and we can also think about that as the opposite of each individual part kind of through this distribution, the opposite of x and the opposite of 3, -x and -3. Okay, let's continue on to our other work. Our first example here is subtracting the expression here. So when we look at this, we see this subtraction here in the middle. If we think about changing this subtraction to an addition, remember we can always say that's adding the opposite. Well, it's adding the opposite of what? The opposite of this group. Alright, so I want the opposite of this group, and we just talked about what the opposite of this group would look like, and so it's the opposite of the individual pieces. So in order to simplify this one, 40 plus 9 plus the opposite of this group. Okay, so this is 30, so the opposite of that would be -30. The opposite of the 2 would be the -2. Again, if you're more comfortable, you can think about this as taking a -1 and distributing in. -1 times 30 would make it -30, and -1 times 2 would make it -2. Now we can go ahead and do this math. I'm going to rearrange this just because it makes it easier for me, because this is going to give me all positive numbers. I can quickly check this one. This is 10. Quickly do this one. This is 7. 10 plus 7 is 17. So sometimes using the commutative property can really be helpful. Alright, so let's come over and look at the next one. We see a similar idea here. We're going to change this to add the opposite, so that's a -4. And once again, we see that where we're subtracting a sum, so that means we're adding the opposite of that sum. And this is really going to actually take us back, now that we're really talking about it and digging into it. I want us to go ahead and justify our steps along the way here. So we want to rewrite this first by thinking about what happens with this opposite of this sum. And now we go back and we think about some of the language we've used around this before, and we think about distributing this in. This makes this the opposite of this sum, is the sum of its opposites. So this would be negative 4x plus the opposite of 11, which would be negative 11. And we go back and we think about the language behind that, and I'm going to ungroup this. There are two things that we do here. One, we use the associative property, but we also use that idea, and we wrote this out this way before. Again, thinking about this is the idea that the opposite of this sum is the sum of its opposites. We also changed our grouping here. So we use the associative property. So one thing that, again, we're going to be talking about over and over again is being able to justify our work. So we change this to add the opposite, which told us that we needed the opposite of this sum, which is the sum of its opposites. Because we took out all the grouping symbols, we can go ahead and kind of regroup them. So now thinking about reordering this, I want to put all of my like terms next to each other. So I can combine 3x and negative 4x. So I'm going to commute those together. Um, 5y has nothing else to combine with. And I have negative 4 plus negative 11. And so when I add these two together, that's going to give me negative 1x plus 5y plus, when I add these two together, negative 7. I have no other like terms I can combine. So again, thinking about proving this step here was the commutative property. And here we combined like terms. And the last thing we can do is, if we really want to, we don't have to do this, just simplifying this down. Negative 1x we know can be simplified. That's just the same thing as negative x. We don't need to show that coefficient of 1. Plus 5y. And if we want to, we can change this addition back to subtraction. So adding the opposite is the same thing as subtracting the positive value. And so we could just write our justification here. Subtraction adding opposite. So as we scroll down here, this is asking us to find the sum by lining expressions vertically. So the idea of any order, any operation, in other words, that's that combination of our associative and distributive property, allows us to kind of think about things a little bit differently if we really want to. Some of us really like to do additions vertically. So if we want to think about this, the first thing we need to do is go ahead and change this to add the opposite and add the opposite, so we can use any order, any operation. And if we want to align our values vertically, I can take this and I can say, well, this is 5a plus 2a plus, looking at our b values, 3b plus negative 4b plus 6c plus 13c. And really think about it as adding up that way. We have 5a plus 2a is 7a plus 3b plus negative 4b, that's negative 1b, plus 6c plus 13c, which is 19c. And again, if I want to simplify this a little bit further, I can get rid of this coefficient of 1 over here, and I could change this addition of a negative back to a subtraction. That would give me 7a minus b plus 19c. And so really we can just see that because of any order, any operation, it just makes it a lot easier here. So our first step here was we changed, so if we wanted to think about our steps here, we changed subtraction to add the opposite. Our next step here was to use any order, any grouping. And then we went ahead and combined like terms. And this last step was we changed subtraction, or adding an opposite to subtraction. So coming down here, same idea. If I want to jump through this, I need to change this. Our first thing, change subtraction to add the opposite. When we do that, we notice that this makes this the opposite of this sum. So when we rewrite that one, we can rewrite it as the sum of its opposites, 2x plus 3y plus negative 4 plus negative 5x plus negative 2. Again, we could think about that if we wanted to as a distribution of a multiplication of negative 1. But realistically, we're justifying this as opposite of sum is the sum of opposites. Now if I wanted to, again, because of any order, any grouping, I could think about this vertically aligned if I wanted to, 2x plus the negative 5x plus 3y, and there are no 3y, so there's really nothing else to add there. And with our constants, negative 4 plus 2, and that's going to give me negative 3x plus 3y plus negative 2. So moving this to vertical allowed us, that was from any order, any grouping. Combine like terms. And if we wanted to, our last step here, negative 3x plus 3y minus 2, we could change the add of the opposite to subtraction. Alright, let's flip on over the page. And so looking at this, it says a stick is x meters long and a string is 4 times as long as the stick. So express the length of the string in terms of x. So the string is 4 times as long as the stick, which the stick is x. So the string is 4 times x. 4 times x. If the total length of the string and stick is 15 meters long, how long is the string? So thinking about this, this gives us something we can set up as an equation. We have x is our stick, so we're looking for the total length. X plus 4x would be equal to 15. So this is string plus stick is equal to 15. If we combine our like terms, that tells us 5x is equal to 15. And we know our inverse operation here is divided by 5. Also, it's pretty intuitive to us that this is going to have to be 3. Looking at this next one, it says that it costs Margot processing fee of $3, so that's a cost. We know that's going to be negative $3 plus $17 per month, so that's going to be negative $17 for every month. So negative $17 times the number of months. Her friend Carissa wants to store a box of hers that belongs in Margot's unit and tells her that she'll pay $1 towards the processing fee, so that's going to be a plus 1, and $3 for every month, so paying her, she's going to be getting $3 for every month, so that's a positive $3 times the number of months. Write an expression in standard form that represents how much Margot will have to pay for the storage unit if Carissa contributes. Then determine how much Margot will have to pay if she uses storage unit for 6 months. So looking at this, her total expenses are going to be the sum of all of these things. So go ahead and write the sum of those things, simplify that expression, and then once you've simplified the expression, go ahead and plug in 6 for M in order to find out how much she ends up paying in total for the 6 months. So looking at this, just adding all of my terms together, negative 3 plus negative 17m plus a positive 3m plus 1. So looking at this, any order, any grouping says that I can go ahead and combine these terms together. So I'm just going to justify this, any order, any grouping. Is negative 17m plus 3m plus negative 3 plus 1. So looking at this, combining this, negative 14m plus combining this, negative 2. So this is combining like terms. And I could change this to subtraction, but I really don't see any use in doing that, considering I'm about to solve the expression by plugging in 6. Negative 14 times 6. And I'm going to want to add a negative 2 anyway, rather than dealing with subtraction. Negative 14 times 6 is going to give me, negative 14 would be 1428. 42 times 2 would be negative 84 plus negative 2. So overall, she has an expenditure of $86. Alright, coming over here, the last thing we want to discuss is multiplicative inverses. So we're showing proof of the multiplicative inverse. We've talked before about how the multiplicative inverse is the same thing as dividing. But we also, if we've thought about it as fractions, we talked about when we divide a fraction, it's multiplying by the reciprocal. So you can see here in this example, they've taken 3, turned it into a fraction, and thought about multiplying its inverse, which would be multiplying by its reciprocal, because dividing by a fraction, we just flip it over, gives me 1/3. And they show proof that their product is 1. So again, thinking back to our additive inverses, they always went to the additive identity, which was 0, and our multiplicative inverses are always going to multiply to 1. And so our proof that they are actually inverses, and then we showed this all the time when we were solving equations, was that we see that we can go ahead and do this with this value, that it makes sure that it gets that multiplication of 1. So that's our proof here in this box here. Then it says use each inverse to write its corresponding expression in standard form below. So what it's asking us to do over here is basically the same idea that we do when we change a subtraction to adding the opposite. And really the goal here is when we're thinking about this, we want to be able to change multiplication or divisions to multiplication so we can use any order, any grouping with our multiplications as well. So instead of having division, we're going to change it to multiplication of the reciprocal. And so we have 12 times 1/3. Again, we've proved that this is the multiplicative inverse, and that they are the same by looking over here at this work over here. So coming down here, just one more example. Our multiplicative inverse is going to be to multiply by the reciprocal, which is 1/5. Our proof is that 5 times 1/5 is the same thing as 5/1 times 1/5, which gives us 5/5, which is equal to 1. So if I wanted to use this idea to write this division as a multiplication, I would want to change it to multiply by the reciprocal, which would be 65 times 1/5. And if we do that multiplication, we're going to get 13. So go through and try the rest of these down here. Maybe when you get to the bottom ones, you might need a little bit of extra support. So let's go ahead and at least get the first two done. So quick check on these first two. With these second two, you're like, oh, well, how do I change this into a fraction? Same thing we do any other whole number. This would be x/1, so our reciprocal would be 1/x. And our proof here is that we would have x times 1/x. Same thing as x/1 times 1/x. We get x/x. And again, we don't have to know the value of that, but anything divided by itself is going to be 1. So if I wanted to simplify this, I'd have 5 times 1, or 5x times 1/x, and we'd get 5x divided by x, which x and x would cancel out, leaving me with just 5. Doing the same thing over here. Go ahead and do this one on your own. Two x/1, so our inverse would be 1/2x. So coming over here, our proof is x times, or 2x times 1/2x would be the same thing as 2x/2x, which again is going to be equal to 1. So we can rewrite this as 12x times 1/2x. That would give me 12x over 2x. Well, the x divided by x is just 1. Those cancel out. 12 divided by 2 is 6. All right, go ahead and flip on over to your alone time and get your work done on your alone time.